Here's something most teams building on language models don't think to check. This is a normal API call. 10,000 tokens of system instructions on top, a short user message at the bottom. Now look at this second call. Same model, same content, word for word. The only difference is which section comes first. But watch the bill. Prompt A costs 0.3 cents. Prompt B costs 3 cents. 10 times more for the exact same content. What's actually going on here? To see where that gap comes from, we have to look at what the model is actually doing every time you call it. Your prompt gets broken into tokens. Every token becomes a position the model has to reason about. And for every one of those positions, the model computes a key vector and a value vector, the KV pair. That's the working memory attention runs on. And it's recomputed fresh every single time. So one request with a 10,000 token system prompt is over 10,000 KV computations, just to get to the first generated word. Multiply that by 1,000 calls a day, and the same system prompt is doing 10 million redundant operations. Most of that math is identical to the call before. The model just doesn't realize it's already done the work. But notice what's true about all that redundant work. Most prompts actually have the same shape, a stable head and a variable tail. The system prompt is the head. It doesn't change between calls. The user message is the tail, and that's the only part that really moves request to request. So here's the move. Take the KV vectors we computed for that stable head and just keep them. Not the text. The actual computed attention state. Store it once, hand it back every time the same prefix shows up. When the next request arrives with that same system prompt, the cache recognizes it. It drops the stored vectors right back into place. Only the new user message needs fresh compute. In one move, most of the work the model would otherwise repeat just skipped. Imagine hundreds of requests are pouring in every minute, each one some mix of system prompt and user message. So how does the KV cache get used? The answer is a prefix tree. It's the structure Anthropic, OpenAI, and Gemini all reach for to solve this exact problem. Here's how it builds up. The first request arrives and the tree is empty. So the system carves a path through it, token by token, from root to leaf. That path is the cached prefix. And along the way, every node on that path holds onto the KV vectors for its segment. The path itself is the index. The vectors hanging off it are the payoff. A second request, same system prompt. This time, the tree already has the path. The lookup walks down it, match, 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 all the way to where the user message branches off. Only that last segment needs fresh compute. That's a cache hit. But what happens when a request shows up with a completely different system prompt? The very first token doesn't match anything the tree knows. So the lookup forks at the root, and the request walks a brand new path. Full compute from scratch. Which brings us back to our mystery of the two prompts with vastly different costs. Prompt A puts the system prompt first. The tree has this exact path already. Every token matches, and we get a cache hit. 80% of the KV computation skipped. Prompt B puts the user message first. The very first token doesn't match anything in the tree, and the lookup stops right there. It doesn't matter that the system prompt is sitting in the cache somewhere. The lookup never gets to it. Full recompute, full price. So we have the same content, same tokens, same model. So why isn't the bill the same? Because the prefix is different, and the cache only ever sees the prefix. That's the rule worth holding on to. The cache doesn't read your whole prompt. It reads from position 0, one token at a time. The moment the first token differs, every token after it is a miss. So let's say you do everything right. Stable content first, cache kits everywhere, costs drop, and the bill looks great. But there's a subtle problem waiting for you. Caches have limits. Memory is finite. If a prefix hasn't been requested recently enough, the tree quietly prunes it to make room for new ones. And the next request that needed that branch starts walking the lookup and gets as far as the cache still holds. Past that point, every token has to be computed fresh. The thing is, nothing tells you when the cache is busted. No error, no warning, just higher latency and a bigger bill, unless you know where to look. Eviction aside, the design pattern follows directly from everything we just saw. Your system prompt goes first, instructions, guardrails, persona. The stuff that doesn't change between requests. That's your stable prefix. Few-shot examples come next. These change occasionally when you update your template, but not request to request. They just extend the shared prefix a little further. And the user content goes last. It's the only part that changes per request, which means it's the only part the model actually has to compute from scratch. When you write a prompt this way, you're really shaping a path through that prefix tree. The longer the shared trunk, the less compute per request. Lower cost, faster time to first token, every call. Anthropic discounts cache tokens by 90%. OpenAI and Gemini offer similar discounts. The cache doesn't read your prompt. It reads your prefix, so put what doesn't change first, and the bill shrinks on every single call.